What if the secret to finding a second Earth isn't looking for another Earth at all? What if, scattered across the galaxy, the one thing that separates a dead rock from a living world is a swarm of tiny, overlooked moons? We're about to explore a fascinating, speculative idea that cosmic life might not always spring up on perfect planets, but could be kick-started by its lunar companions. For decades, our search for life has been a search for planets. We've been looking for a single lonely marble, a pale blue dot orbiting its star at just the right distance. But the universe might be far more clever and way more collaborative than we ever imagined. The story of life may not be written on a single world, but across an entire system, with the key being not just the planet, but its team of tiny architects. So, forget the idea of a solitary Earth 2.0 for a moment. Instead, picture a planet cradled by a whole swarm of moonlets, maybe a dozen, maybe 100 tiny gravitational shepherds, all working together. These aren't the big, singular moons we're used to. They're a collective, a cosmic committee of world builders. Now, this sounds like science fiction, but it's an emerging hypothesis that could challenge our understanding of what makes a planet habitable, potentially transforming barren super-Earths into stable, life-sustaining worlds. It suggests that the most common cradles of life out there might not be planets that were born perfect, but planets that got a major assist from their many moons. Ever since we started searching the stars for other homes, our strategy has been guided by a simple, elegant idea: the habitable zone. You've probably heard of it as the Goldilocks zone. It's that narrow, orbital band around a star where the temperature is just right, not too hot, not too cold, for liquid water to exist on a planet's surface. Find a rocky, Earth-sized planet in that zone, and you might just have a winner. This is the blueprint that has guided multi-billion-dollar telescopes and decades of research. We are essentially looking for our own reflection in the cosmic ocean. The problem? The universe has repeatedly shown us it's not that simple. Our own solar system is a graveyard of Goldilocks failures. Take Venus. It's almost identical in size to Earth and sits right on the inner edge of our Sun's habitable zone. By the simplest definition, it should have been a paradise. Instead, it's a hellscape, crushed under an atmosphere 90 times thicker than ours, with surface temperatures that can melt lead. A runaway greenhouse effect boiled its oceans away and sterilized the entire world. On the other side, there's Mars. The red planet sits on the outer edge of the habitable zone. Evidence carved into its surface tells us it once had flowing rivers, vast lakes, and maybe even an ocean. It was a water world for a while, but it couldn't hold on. Being small, its internal heat died out, its magnetic field sputtered, and the solar wind stripped its atmosphere away, leaving it a frozen, barren desert. Both Venus and Mars were in the right place, but they were missing all the other critical ingredients. And that's the real challenge of habitability. It isn't just about location. A planet needs a stable axial tilt for moderate seasons. Our own moon is the gravitational anchor that stops Earth from wobbling all over the place. A planet needs a strong magnetic field to shield its atmosphere. It needs active geology, like plate tectonics, to regulate its climate over millions of years. The list of requirements is so long and so specific that finding a planet that ticks every single box feels less like a scientific search and more like trying to win a cosmic lottery. But what if we've been trying to win a nearly impossible lottery while ignoring a different game the universe is playing everywhere? So, what if the key to all these complex requirements, a stable climate, a thick atmosphere, the right chemistry, isn't something baked into the planet itself? What if it's an external service provided by a committee of tiny, loyal companions? This is where our story takes a sharp turn, away from the lonely planet and toward the idea of a habitable system. The new and highly speculative idea is that small moons, or moonlets, could be the galaxy's unsung planetary engineers. When we say moonlet, we're not talking about something huge like our own moon. Think smaller. Think of a whole collection of them, maybe dozens, ranging from large asteroid-sized bodies to small dwarf planets. These are often the leftovers from a planet's violent birth. Our own moon is thought to have formed from a disk of such debris after a huge impact. In our case, those moonlets eventually clumped together into one large satellite. But what if, in other systems, they didn't? What if they stayed as a stable orbiting swarm? This hypothesis proposes that such a collection of moonlets might collectively perform the stabilizing functions we thought required a single large moon, and maybe even do more. In this picture, they aren't just passive orbiting rocks. They're active players in their planet's evolution. Through their combined gravity, they could theoretically sculpt a planet's environment, help build its atmosphere, and guide it from a barren rock into a cradle for life. This shifts our whole perspective. We'd stop looking for one perfect object and start looking for a perfect configuration. A planet with its team of lunar architects. It implies the galaxy isn't just filled with failed Earths. Instead, it might be full of fixer-uppers, planets that got a helping hand from their own moons. The first job of any cosmic engineer is to create stability. Here on Earth, we have predictable seasons and a relatively stable climate because our planet's axis is tilted at a steady 23.5 degrees. But that stability isn't a given. Without our moon, gravitational nudges from the Sun and Jupiter would cause Earth's tilt to swing chaotically over millions of years, from 0 to maybe 85 degrees. The results would be apocalyptic. A planet with zero tilt has no seasons. A planet tilted on its side has extreme seasons, with each hemisphere locked in either decades of constant sun or decades of freezing darkness. Life as we know it couldn't survive that. Our moon acts as our gravitational anchor. Its pull on Earth's equatorial bulge keeps our world steady. So, how could a bunch of tiny moonlets, each with a tiny fraction of the moon's mass, possibly do the same job? The theoretical answer lies in the power of the group and a phenomenon called orbital resonance. Imagine one moonlet. Its gravitational pull is a whisper. But now imagine a dozen of them, all orbiting at different distances and speeds. The idea is that over time, their orbits could sync up, settling into a complex but stable pattern. One moonlet might complete 3 orbits for every 2 of another. These synchronized gravitational nudges, though small on their own, would add up. They'd create a stable, interconnected web of gravity around the planet. Instead of one big anchor, you'd have a distributed network of smaller ones. This committee of moons would, in theory, exert a collective stabilizing force on the planet's spin. Their combined resonant pulls could dampen the wobbles caused by its star or other planets. While our only working example of this is a single large moon, some models suggest a distributed system of moonlets might be able to create a more nuanced and resilient system of stabilization. This gravitational harmony would be the first act of world building, laying the foundation for a stable climate where life could eventually get a foothold. With the planet stable, the moonlet engineers could turn to their next big task: building and maintaining an atmosphere. An atmosphere is a planet's lifeblood, regulating temperature, shielding from radiation, and providing air to breathe. But atmospheres are fragile. This is where moonlets could play their most creative role, acting as both architects and guardians. Their first act is one of cosmic delivery. Moonlets are often just leftover planetary debris or captured asteroids and comets, which means they are frequently packed with volatiles, the building blocks of an atmosphere. We're talking frozen water, ammonia, methane, and carbon dioxide. In the early days of a system, a steady rain of these moonlets would be like a cosmic delivery service. Each impact would release its cargo of frozen gases and water, gradually seeding a dry, rocky world with the raw materials for an atmosphere and oceans. But building an atmosphere is only half the battle. You also have to keep it. A planet's air is constantly being blasted by stellar wind, which is what happened to Mars. Here, a system of moonlets could help in a couple of ways. Their gravity would pull on the planet's gaseous envelope, creating atmospheric tides. This constant churning could drive weather patterns and transport heat around the globe, keeping the atmosphere dynamic and healthy. Then there's the gift of heat. For worlds orbiting far from their star, any surface water should be permanently frozen. But if a planet has moons, it has another potential energy source: tidal heating. As a moon orbits, the planet's gravity flexes it, generating internal friction and heat. We see this with Jupiter's moon Io, which is incredibly volcanic because of this effect. A planet with many moonlets would experience the reverse. Their combined tidal forces would pull on the planet itself, potentially warming its interior. This extra internal heat could help drive volcanism, which releases gases to replenish the atmosphere. For a planet on the cold edge of the habitable zone, this little bit of tidal warmth could be a contributing factor in keeping its oceans liquid and its climate temperate. Through this combination of delivery and dynamics, a swarm of tiny moons could help turn a barren rock into a more vibrant world. This idea, as cool as it is, would just be a fun thought experiment without some data. And while we haven't found a system like this yet, we're starting to see tantalizing clues that the universe might indeed be building worlds this way. As of late 2025, no exomoons have been definitively confirmed, but the search is heating up. One of the most exciting pieces of evidence comes from the James Webb Space Telescope. In a landmark discovery, JWST directly measured a massive disk of dust and gas encircling the young exoplanet CT-CHA-b. This is a circumplanetary disk, a moon-forming disk. For the first time, we are literally watching the raw materials of a lunar system taking shape around a distant world. We can even see that it's rich in the carbon-based molecules that are the precursors to life. It's a snapshot of the very beginning of the process. In another surprising find, JWST detected methane and aurorae on isolated brown dwarfs, or failed stars. This was strange, since there's no star to power these aurorae. One fascinating hypothesis is that they might be triggered by a magnetic interaction with an unseen, active exomoon. It's an indirect but powerful clue that moons can be active players in their system's physics. Detecting these moonlet systems directly is the next big challenge. For that, we're looking to the next generation of observatories. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will be a game-changer. It will use a technique called gravitational microlensing that is so sensitive, it's expected to be able to detect exomoons down to the mass of Jupiter's moon Ganymede. Early predictions suggest that over its main mission, Roman might only find one such exomoon, but that's based on the assumption they're as rare as the big moons in our solar system. If this new theory is right, and systems of moons are way more common, Roman could open the floodgates. The tools are finally catching up to the theory. If this theory of lunar engineering holds true, the implications are just staggering. It would completely redefine our search for life and could dramatically expand the number of potential habitable worlds in the galaxy. We've been searching for needles in a haystack, rare, perfect planets. But this theory suggests the galaxy is full of haystacks that have learned to build their own needles. Think about it. The number of known giant planets in the habitable zones of their stars is already significant. While gas giants aren't habitable, they could host families of large rocky moons, warmed by tidal forces and cloaked in thick atmospheres. The habitable zone is no longer just a narrow ring around a star, but a vast volume of space surrounding any planet with a robust lunar system. Suddenly, the cold outer regions of a solar system become potential homes for life. A planet we would have dismissed as a frozen ice ball could be a thriving water world if its internal temperature is maintained by the constant gravitational kneading of its many moons. This forces us to change our entire search strategy. We'd no longer prioritize only single Earth-sized planets. The most promising targets might become planets that show signs of a complex system around them. We'd look for the subtle wobbles that indicate multiple companions, or the tiny secondary dips in light as a family of moons transits a star. The ideal candidate for life would no longer be a lonely world, but a planet at the center of a busy, dynamic, gravitational dance. It also just fires up the imagination. What would it be like to stand on the surface of a world like that? You'd look up at a sky filled not with one moon, but with dozens. Some might be bright crescents, others faint, star-like points of light, turning night into a perpetual silvery twilight. These would be worlds born not of quiet solitude, but of a noisy, collaborative, cosmic family. The galaxy may be far more hospitable and far more wonderfully strange than we ever dared to believe. We began our journey looking for another Earth, a singular planet that somehow won the cosmic lottery. But the universe may not always rely on pure chance. It might be a more creative place, using the most common of materials, the leftover rubble of planet formation, to construct its masterpieces. The idea that tiny moons can be the architects of habitable worlds is a profound shift in our cosmic perspective. It suggests that habitability isn't always a static property of a planet, but an emergent feature of a whole system. The search for life, then, is no longer just a search for planets. It's a search for families of worlds, for planets and their moons working together. This theory is still in its infancy, and it will take powerful new telescopes to see if it holds water, but it opens up a breathtaking new realm of possibility. What do you think? Could a swarm of tiny moons be the galaxy's preferred method for building habitable worlds? Let us know in the comments below.